Welcome to our next lesson on the geometric sequence. We're going to begin by doing a paper folding activity. So I want you to take out any piece of paper, a loose leaf or just a white piece of paper, and we're going to fold it in half and try to do it more than 7 times or at least 7 times. And then each time we fold the paper, we have to rotate it 90 degrees. And we're going to record this in the table below as the number of folds, and then how many number of layers we have after each fold. Now, if we just take one piece of paper, we're just going to say there's one layer, which is your one piece of paper. Now, if we take that piece of paper and fold it in half right down the middle, that's one fold, and then you're going to see 2 layers, one on each side of the fold. Now we're going to fold it again. And if you do that, you're going to have 2 folds now. And if you were to open up your piece of paper, you're going to see 4 layers. That'll be kind of like the 4 rectangles that you see that make up the piece of paper. Now do this again, and let's just do this another few times where you have 6 folds. And then record your answers and the number of layers that you see. So after 3 folds, you should get 8 layers. After 4 folds, you just get 16, then 32, and that last one is 64 if you were able to make it that far. But if we analyze to see the number of folds compared to the number of layers, this is called a geometric sequence because we are going to multiply the first term by some number to get the second term. So in order to get from 1 to 2, we're going to multiply this by 2. In order to get from 2 to 4, we can also multiply it by 2. 4 to 8, we multiply 4 by 2, and so on and so forth. And if you look at this pattern, we can see that if we would just keep multiplying by 2, we're going to get the next number. So in summary, a geometric sequence is formed by multiplying each term after the first term by some constant to determine the next term. So for example, the sequence 3, 9, 27, 81 is a geometric as each term is multiplied by 3. And the first term is T1, which is equal to 3. The multiplier 3 is called the common ratio, and we denote this by an R. So this R is what we're going to multiply by to get the next term. And your common ratio is any non-zero real number that can be found by dividing any term by the preceding term. So let's take a look at these sequences. For the sequence above, if you want to find what our next term is, you just take one of the terms, 9, and divide it by the first term, which is 3. And then you're going to know what our R is. So R is going to be 3. You could do that using 27 and 9 instead. So we could have used 27 divided by the next term, or the term before that, which is 9. And you're going to get 3, which would tell you what your common ratio is. So for the following geometric sequences, we're going to find that common ratio R by taking one of the terms, let's say 16, and then dividing by the term that's right before it. So that'll be 16 divided by 4. So R is 4. We could have also done 64 divided by 16 and gotten the same answer. For the next one, we can do 1.5 and then divide it by the term just before it, which is 0.5. This is 3. And then lastly for C, I'll take 1.6 divided by the term just before it. So 1.6 divided by 2, this is 0.8. Here's some other examples. 4, 12, 36, 108 is an infinite geometric sequence because it continues on forever. If it ends at 108, this is a finite geometric sequence because the sequence stops after some number. Now, the next type, we have 2, 10, 50, 250, 1,250. This is an increasing sequence because the terms increase. And it's also divergent because its terms do not approach a constant value. So that just means that we're just going to keep increasing, going on forever, and it doesn't tend to some number. Now, looking at the next one, we have a decreasing sequence for this one because the terms are decreasing. But this is convergent because the terms are approaching 0. As we go along in the sequence, it's getting so small, smaller, smaller, and smaller, that it's going to become 0, or very, very close to 0. And then lastly, we have a neither increasing nor decreasing sequence here because we alternate from positive to negative numbers. And because of that, it's also divergent because it's not going towards any certain number at the end. So take a note of these different types of geometric sequences and its properties, because you need to be able to determine if a sequence is infinite, finite, increasing, decreasing, or divergent or convergent. Now I want you to think, why must R be non-zero? If R was 0, all the terms would be 0 because you would have to keep multiplying by 0. Then it's not really a sequence anymore. All right, so let's do some actual examples of this. Determine the 10th term of this sequence. So the first thing we're going to do is determine what R is. I'm going to take the second term and divide it by the first term, which is -3. That means we're multiplying by -3 to get the next term. So this is T1, that's T2, T3, T4. T5 is what we need to find, 6, 7, 8, 9, and then our final answer is T10. So for T5, it's going to be calculated as -54 times -3, which is positive 162. For the next one, for T6, if I multiply 162 by -3, we're going to get -486. If I multiply -486 by -3, I'm going to get positive 1,458. Then I'm going to multiply this by -3. I'm sure you get the pattern. So I'm going to multiply that by -3. And our final answer for T10, I'm going to multiply 13,122 by -3. We're going to get -39,366. And is this sequence increasing, decreasing, and convergent or divergent? Because we're alternating between positive and negative numbers, this is a neither. It's neither increasing or decreasing. And because of this, it's also divergent. It's not tending towards any certain number. Now, for example 2, create a geometric sequence whose 6th term is 27. So we're going to have to work backwards here. This is your 6th term. 5th, 4th, 3rd, 2nd, and 1st. Now in this case, I suggest that you pick an R, and an R has to be able for you to divide to get the previous term. So I'm picking R equals 3. You could have picked a different number for sure if you wanted to. You could have picked something like 9 because we can do 27 divided by 9 as well. I'm just going to choose 3. So 27 divided by 3 is 9. Then 9 divided by 3 is 3. 3 divided by 3 is 1. 1 divided by 3 is a third. And 1/3 divided by 3 is 1/9. So this is one example that we could have used. You just pick an R that you could use to divide the term that was given to you. Again, you could have used R equals 9 if you wanted to. I just picked R equals 3. So here is the general term of a geometric sequence. We're going to use this formula. T1 is the first term, R is your common ratio, Tn is the nth term or general term, and n is the number of terms, where n is a positive integer. So let's use this. to look at other examples. So example 3, we have a finite geometric sequence where T1 is 7 and T5 is 567. We want to find T2 and T6. Now the first thing we need to do is find R. And this is our formula we're going to use. So to find R, let's think about what we have. We have a T1, it's 7. Instead of writing just Tn, we could be more specific and look at T5. That means n is equal to 5, and the only variable missing is going to be R. So I'm going to fill in the information we have. So we're going to do T5, T1, leave R alone, and then n is 5. I'm going to divide both sides by 7, and we're going to get 81. And then 5 minus 1 is 4. I'm going to take the fourth root on both sides. So you can get R by itself, and this is going to be 3. So R is equal to 3. Now it's pretty easy to find T2 and T6. So T2 is going to be the first term multiplied by R, so that's 21. Then to find T6, I'm going to take T5 and multiply it by R. And those are our two terms. T2 is 21 and T6 is 1,701. Next type of question, we know the last term is 45,927. We want to find the number of terms there are in this sequence. So we're finding n. So I'm going to use the same formula. In this case, my Tn is the very last term, so that's 45,927. And T1 was given to us in the original question, which is 7. We know what R is 3, and I don't know what n is. So I'm going to divide both sides by 7. In this case, I'm going to rewrite 6,561 with a base of 3. And you can just play around with the calculator for this. And you're going to find that 3 to the power of 8 is going to be the same thing as 6,561. Now, I don't need to think about these 3's anymore and just focus on the exponent. So n is equal to 9. There are 9 terms in this sequence. We're going to do 2 more examples. So example 4, Statistics Canada estimates the population growth of Canadian cities, provinces, and territories. The population of Nunavut is expected to grow annually by 0.8%. In 2009, its population was about 30,000. We want to estimate the population each year to the nearest 1,000. And we're looking for the year 2013. So if we're looking about each year, this would be T1 as our first term, or as our 1. So this is their first year, where n is equal to 1. And then if we count the number of years after that, this will be n equals 4. It's 4 years after 2009. And the population associated with this 2009 is 30,000 people. So this is actually our T1, the first term. And our terms are all going to be about population. So I'm going to rewrite this out. So we have T1 is equal to 30,000. R is also given to us as well because it's saying that the population is expected to grow by 0.8%. So if I change 0.8% into decimal, it's going to be 0.008 by dividing by 100, because we need that in decimal. Now for our R, because this is a rate, just like how in taxes, I do want to include a 1 in front of our decimal place because this will include the 30,000 in it. And if I don't include 30,000, of course it wouldn't make sense because the numbers would get smaller, smaller, and smaller when our population should be getting larger. So by adding this 1 in here, I'm going to include that 30,000 in there, and we're going to keep including the previous number after that. So I'm just going to say this is to include the original 30,000 people. Okay, so we're going to find what T4 is, because that will give us the population in 2013. So T1 is 30,000. The next thing I need to fill in is R, which is 1.008. And then n minus 1 is our exponent, which is in this case 4 minus 1. Now we're going to find 1.008 to the power of 3, which is 1.024192512. I'm just keeping as many decimal places as I can. And we're going to multiply this by 30,000. So that's 30,726 is our population in 2013. Now let's do it for 2049. The first thing we're going to do is find what n is, and this would be the year we're looking for minus our starting year, which is 2009. So this would be 40 years later. So we're looking for T40 then, and we have T1, which is 30,000. We have R, which is 1.008, and then n minus 1, which is 39, because that's 40 minus 1. I put this in a calculator, so remember to find 1.008 to the power of 39 first, and then multiply by 30,000. I'm going to get 40,934 people in the year 2049. Last example. So sometimes you use a photocopier to make enlargements or reductions. Suppose the actual length of a photo is 25 centimeters and the smallest size that a copier can make is 67% of the original. What is the shortest possible length of the photograph after 5 reductions? And we're going to answer to the nearest tenth of a centimeter. All right, so our first T1 is going to be 25, and all our terms are going to describe the length of the photo. Our n, well, let's think about this. So we have a T1, which is 25, and we're talking about 5 reductions. So this is 1 reduction, 2 reductions, 3 reductions, 4 reductions, 5 reductions. So I'm actually looking for T6, so n is equal to 6. And then for our R, we're going to make a smaller photo of the original, which is going to be 67% of the original. I'm going to leave that as 0.67. In this case, you don't want to put a 1 in front of your decimal because we're trying to make reductions, making it smaller, smaller, and smaller. All right, so this is our formula. Tn is what we're looking for, but this case is T6. You're looking for the term after 5 reductions. T1 is 25. Our R is 0.67. Exponent will be 5 because that's 6 minus 1. So 0.67 to the power of 5 multiplied by 25. It's going to be 3.4 centimeters. This is going to be the length of the photograph after 5 reductions.